What is a magnetic moment really? If you stop staring at symbols and try to see the thing itself, in the energy filament theory, a magnetic moment is the tiny swirl that an electron's internal ring current scratches into the surrounding energy sea. A faint circular bias that quietly tells the universe, I like to spin this way. Start again from the electron as a loop. The ring itself is not a little ball spinning like a planet. Its overall shape sits almost fixed in space. What actually moves is energy flowing along that ring, lap after lap. Like a neon halo on a wall where the glass never moves but the bright dot of light keeps chasing itself around. That steady circulation along the loop is the ring current. And wherever that current gently twists the nearby sea into a tendency to circle, the trace it leaves is what we call the magnetic moment. This trace looks nothing like the sharp, straight folds of an electric field. Electric texture is like cloth pressed into clear pleats, visibly tighter in some directions and looser in others, easy to draw with arrows. Magnetic moment is much softer. It barely changes how tight the sea is up and down. Instead, it makes a small ring of fluid around the loop wanting to drift sideways, to move around rather than just in or out. Picture putting your fingertips on a still pond and giving one light circular stir. The water does not explode into big waves. It simply picks up a delicate, shallow swirl that slowly fades. That small swirl is the closest everyday picture of a single magnetic moment at work. Almost every kind of particle has some magnetic moment, but its strength can be large, tiny, or almost invisible. The key thing is not just how strong the swirl is, but that it has a clear, well-defined direction. The arrow of the magnetic moment tells the sea which way the loop's internal current prefers to go, carving a subtle this way around tag into the medium. That tag turns a characterless little blob into something with a microscopic facing, a built-in orientation that other loops can, in principle, notice. Now imagine many such loops packed together, as in a piece of iron. If their magnetic moments point in random directions, the tiny swirls cancel and the material behaves like ordinary metal, magnetically boring. But if enough of those internal currents happen to line up, all their faint circular scars in the sea reinforce one another. Each swirl is tiny on its own. Yet when millions of them stack in the same orientation, the region acquires a strong, coherent swirling pattern. That large-scale, ordered swirl is what you experience as a bar magnet with a clear north and south. Not one heroic particle, but a whole crowd of magnetic moments standing at attention. Magnetic moments also controls something more intimate and short-range. Whether nearby particles can gently line up their internal directions and form basic, near-field couplings. It is not like an electric field that can reach across space and shove charges around. And it is not like gravity that touches everything all the time. It only really matters when particles get very close and when their moments point in compatible ways. In that tiny neighborhood, your loop's swirl acts like a quiet suggestion. This is the way I'm going. Do you want to match me? If another particle with a similar moment gets close enough and can adjust to that preferred orientation, the two may lock into a slightly lower energy configuration. A small but crucial binding that contributes to whether a material ends up paramagnetic, ferromagnetic, or almost non-magnetic. You can wrap it up like this. A magnetic moment is the faint circular scar that an internal ring current leaves in the energy sea. It is not itself a big push or pull like the electric field around a charge. And it is not the whole story of magnets grabbing nails. But it is the directional tag that makes those later effects possible. It marks each particle with a tiny arrow that says, my swirl is oriented like this. Line up enough of those arrows and magnets appear. Let only a few interact at very short distances and they quietly decide which particles can align, which structures can lock, and which will just slide past each other. Tap follow, share it on New Physics, Clear Universe.